Okay. Hello everyone. Welcome to the week 12 of problem solving session for the NPTEL course on computational complexity. In this week, we'll look into the interactive proofs, the public coin and private coin protocols, and we'll look into the definitions, the basic definitions of these, and some examples on based on that. Before we define anything, I would just like to recall that the next session, which is an extra problem solving session, will be on upcoming Wednesday, which is 15th October, from 7 p.m. to 9 p.m. Okay, and okay, just let me just make sure that this is being recorded. Okay, yeah. Okay, so last time we saw what is called communication complexity, and so where basically we had a function f, and part of this input x was known to Alice, and the other part was known to Bob, and their goal together was to compute f of xy, and they're allowed to make some queries. So, and it's not necessary that there's an order between them, that Alice's query need not be necessarily followed by Bob's queries, and so on. So we also saw the tree corresponding to this. Okay, and okay. So now we're going to define this new model, which is slightly, although it has slight overlap with the ideas in communication complexity, it's a different class. So how do we define interactive proofs? Or IP. So you say that a language L, which is a decision language, is an IP if we have a verifier P and a prover P. Okay, and the verifier is honest. Okay, so the verifier has to truthfully determine whether if x is in the language, then we want the verifier ideally to always be able to detect that x is in the language, and if x is not in the language, we want the verifier to be able to detect that. That's the ideal situation. Okay, and how does verifier decide whether x is in L? Again, they're allowed to have some communication. So verifier can ask some queries to the prover, and the prover can answer back to the verifier based on the information. Okay, I think there's some lag in okay, now it's okay. And then based on these, the verifier can ask further queries. So Q2 could be based on Q1 and the previous answers, and the prover can respond to that, and so on. So this is a communication that happens between them, and at the end of the day, if x is in the language, then there should be a series of queries and answers to it, such that the verifier is convinced that it is indeed an instance of the language. So if x is in L, then there exists an exchange of messages between them. So there exists some queries Q1, A1, Q2, A2, and so on between the verifier and the prover, such that the verifier accepts x, and if x is not in the language, then no matter what series of messages get exchanged between them, no prover should be able to convince V that X is in the language. So that does not exist. Q1, E1, and so on, a series of exchanges between them, such that sorry. So in other words, if X is in the language, we always want the verifier to accept. If X is not in the language, we always want the verifier to reject. Now this prover P is an all-powerful prover. That is, there's an infinite computational power that P has, and the verifier P is a polynomial time verifier. So that immediately means that these queries and answers cannot be more than poly-sized, because the verifier cannot run that long. However, the prover can do an infinite amount of computation at their end. Okay, so this is what is called DIP, where the D stands for deterministic. And as you can see, any language in NP is naturally contained in DIP. This is something we know because in that case, the prover can just send the certificate, right? So we know that if a language is in NP, there's a small certificate using which the verifier can check whether it is in the language. So this is just a one round protocol. So okay, so this denotes the number of rounds. Okay, and in general by DIP we mean we mean k number of protocols and k number of rounds, and generally the most commonly used term here is poly. So if we don't write anything, we basically mean that these are polynomial number of rounds. So that's the convention that we're going to follow. Okay, and we also know that this containment is true in the other direction as well. So in fact, DIP is also contained in NP. This is because if X is in the language, the prover, since the prover is all powerful, the prover can at its end come up with this series of queries and answers. So think of this whole thing as a certificate, and just send this to the verifier, and the verifier will be convinced that X is indeed in the language. So so therefore this DIP, although we expected that since it has so many in NP you are only allowed to have one communication, which is that the prover just sends the certificate to verifier, and the verifier is going to verify it in polynomial time. Whereas this seems to be a more powerful model at first sight, because you are allowing so many rounds of communication. But it turns out that it does not add to the power. In fact, it's the same. It's still the same as NP. So now what do we do? Because we started off with the idea that this communication could help us have more power in some sense. So the idea is that instead of forcing the verifier to be deterministic, so this is a deterministic verifier, what if we allow the verifier, we give it a power of randomness. So what if we allow that this is a random verifier? Okay, so now is this new model more powerful? So this is what is called interactive protocol. The only difference here that we have made is that instead of it being a deterministic verifier, it is now a random verifier which can toss random coins, and whether these coins are public or private that something will define. So by public we mean that the prover also knows what the random coins are, or the random bits that have been tossed. The private coin protocol means that only the verifier knows what are the random coins that are being tossed. We'll define this in detail shortly. So there are two definitions of it: public coin, two variants of it, and private coin. We'll get into the details of it later, but right now let's just focus on this IP class. Okay, so now the question is, um, now that we have given this additional um, power to the verifier, that we're allowing it to be randomized, is this model more powerful, and if so, how powerful is this? Okay, so okay, so let me just define this formally. Okay, so we say that L is in IP if whenever X is in the language, there exists a series of transcripts that exchange of messages between the prover and verifier, such that the verifier B accepts with probability at least 2/3, and if X is not in the language, then yeah, for all possible exchange of transcripts, the probability that, so let me just write it, the probability that V accepts is at most 1/3. Okay, so so just to compare this with the previous definition of DIP, when we had a DIP here, we had acceptance probability of 1, and if X is not in the language, then we had acceptance probability of 0. Whereas since now we have this now that the verifier has access to random coins, so these AIs, which are the messages that are sent by verifier, these are random coin tosses. And now if X is in the language, we are relaxing the acceptance probability to 2/3, and also if X is not in the language, we are allowing the error to be 1/3. Okay, so natural question at this point is that this part of the definition that's being written is very, very similar to one of the randomized complexity class that you have already seen in the course, which is what is called BPP. So what is BPP? So we say that L is in BPP if X is in the language, then probability that M accepts, where M is a deterministic is a probabilistic polytime Turing machine, is at least 2/3, and if X is not in the language, then the probability that M rejects is at least 2/3. So these two conditions seem very similar to DIP, to IP. So could it be that that BPP is indeed equal to IP, or if not, then is any containment known? So as an observation, we can show that BPP is in IP. Yeah, this is because you don't allow so many, if you just don't allow that these many exchanges of messages, and just let the verifier make a guess, and without any communication decide whether to accept or not. Then, so without even using the prover, will end up accepting an X in the language with probability 2/3 and rejecting an X not in the language with probability 2/3. So without using any power, we can simulate BPP using IP. Therefore BPP is contained in IP. This is a a straightforward observation. And so to draw the picture, we have P, yeah, and P is contained in NP. We know BPP contains P, but we don't know the relation between NP and BPP. By Kaplipton theorem, we know that BPP is in sigma 2, which in turn is in pH. Okay. Now, where does IP lie? So we know that this is nothing but DIP. This is something that we showed just now, and this observation here basically says that PPP is contained in IP. Okay, and it can also be shown that NP is contained in IP. Okay, so again we know that these two classes are contained in IP, but we don't know, we still don't know the relation between these two, and similarly NP is contained in sigma 2. So this is where we are. The question is, how do we upper bound this? So is it that IP is contained in pH, or is IP contained in EXP, and so on? So on one hand we know that it it captures BPP class, but how large could it be, or could it be just as powerful as BPP, like it so happened in this case? So it turns out, I think in 1992, it was shown that IP is in fact equal to P space. So any language which has an interactive proof, so whenever we don't write the number of rounds, like I said earlier, we mean polynomial number of rounds. So naturally the length of the queries are also restricted, and the verifier is also is a polytime verifier. Okay, so although we'll not be writing this poly, implicitly we always mean that the number of rounds is polynomial many. So yeah, we know that this in fact is equal to the class P space. Okay, so we'll see one direction of this proof later on, but I'll not prove this right now. We'll get to it in a while. Okay, so moving on to the questions. So here are a few statements about the interactive proofs IP, and we want to identify which of these are true. Okay, so multiple of them could be true. I'll just wait for a couple of minutes and discuss the solution. Okay, so this is something that we just saw. So we know that BPP is contained in IP, so this statement is true, and we also saw that DIP is equal to NP, and NP is contained in P space, therefore DIP is contained in P space. And now we are left with two statements. So let's look at the first one. The permanent can be computed by a polynomial sized interactive proof. So turns out, this is something that we saw in the lectures. You might have seen that SharpSat can be solved in IP with polynomial number of rounds. So SharpSat is complete for, we also know that SharpSat is complete for sharp P, and permanent is also complete for, is also sharp P complete. So we've seen the reduction between between permanents to matchings to counting the number of perfect matchings. So but anyway, we don't need to get into the actual reduction. We'll just use the fact that it's sharply complete. So because you have an interactive protocol for SharpSat, which is a sharply complete problem, you can use the same reduction to get a protocol for the permanent problem. So therefore we know that permanent is also in IP. So this statement is also true. Now we'll verify the last statement, which is AM with polynomial number of rounds is in IP. So let us recall what is AM. So okay, so we have defined this class IP with poly number of rounds. Now there are several questions that we could ask um, at different points. So for example, if I restrict the notice that similar to to the idea in communication complexity, where there is no rule in which the communication must take place. That is, Alice can speak as many times, followed by which Bob can respond to it, and it's not necessary that every query of Alice should be responded by a query of Bob. So similarly, we have the same the same idea in interactive protocol as well. It's not necessary that the communication must go on bit by bit, that every bit of message by the verifier need not be responded by the prover. Okay, so and also there is no rule about who speaks first. It could be that the verifier speaks first, or it could be that the prover speaks first. So it's up to us to decide the protocol. Okay, so if let's talk about 2 rounds of communication. So what happens in 2 rounds of communication? What are the possibilities? Either the verifier speaks first, post which the prover responds to it, or the prover speaks first, after which the verifier responds. Okay, and at the end of these 2 rounds, the verifier is going to decide whether to accept or not. Okay, so yeah, so the question is, are these two as powerful? Notice that I'm not considering the cases where both communications were done by verifier or both communications were done by sorry yeah or both the communications were done by the prover, because I can just concatenate these 2 queries, Q1 and Q2, and consider it as a single query by the verifier. And similarly, we can concatenate the 2 queries of the prover and consider it as a single query. So we'll not really count this as 2 rounds of communication. Okay, so we'll just stick to these two. Okay, and yeah, okay, so now these kinds of models where the verifier speaks first, or sends the random coin tosses, followed by which the prover responds, these are called Merlin-Arthur protocols. And yeah, although I defined it like this, this is just Merlin-Arthur protocol with 2 rounds. You can also think of an extension where there is a series of communication where verifier followed by prover and so on. Okay, so there could be k rounds or any number of rounds that you can define. This is just a Merlin-Arthur protocol with 2 rounds where the verifier speaks first, and the other case where the prover speaks first, this is what we'll call Arthur-Merlin protocol with 2 rounds. Okay. So now the question is, which of these is more powerful? Are the languages that are there in MA with two protocols also there can be simulated with an Arthur-Merlin protocol with two rounds, and vice versa? So that is something that which is a natural question to ask. And yeah, so just to yeah, yeah, just to recall that this the Merlin here corresponds to the verifier and Arthur here corresponds to the prover. This um, yeah, so the Indian version of this is something that's called the Akbar Birbal thing, where um, Arthur wants to know an answer to something, and Arthur is only going to verify, where Merlin uh, is his minister who can who can use all sorts of computational power and try to convince Arthur uh, whether the statement is true or false. So it just refers to that. Okay. So, and it can also be shown that an Arthur-Merlin protocol with polynomial number of rounds is an IP, because um, yeah, so this is where the verifier speaks first. Yeah, and by IP we anyway mean polynomial number of rounds, and yeah, okay. So I'm not sure whether this containment is strict, but an IP protocol is basically an AM protocol. Now yeah, we also know that AM is contained in MA. So you can think of AM, AM, and so on. This will be equivalent to replacing um, every MA here with an AM. So this will be AAM, AMM, which is same as AM, AM. This is because the two consecutive queries of Arthur can be merged together to make a single query, and the two consecutive queries of Merlin here could be clubbed together to make a single query. So this class AAM AMM is same as AMAM. Okay. So these are the concepts that we saw in the class. I'll not get into the proof of this because into the details of this because this was already covered, but we'll look into some examples and some questions for understanding this. So I'll just read out the question. So in the IP model, as we saw, the verifier was randomized. But we didn't make the prover randomized. The prover was still deterministic. So let's say the prover is also allowed to be randomized. Okay, so we have our verifier V and the prover P, and this was a randomized verifier. This was earlier a deterministic prover. Okay, now let's say that we give more power to the prover, so we allow the prover also to be randomized, and let me call this IP star. So this is our new definition where the prover is also allowed to be randomized. The question is IP star strictly more powerful than the original model IP? Because we have allowed the prover to be to have more power in some sense. Okay, so it turns out that um, this is this is no more powerful than the original protocol that we have. In fact, IP star is same as IP. So also note that this is not a general class. This is not a no as such. I'm just choosing to call it IP star for now, but this is I don't know if this. I mean, it's not a general studied name as such. Okay. So why is this? Because we defined our prover to be all powerful. Okay, so the prover can do all sorts of computation at their end and decide what to respond to the verifier's query. Okay, so even if you give a randomized power to it, it it could have anyway gone through all possible um, I mean computations, and then chose what to respond with. So the randomization here does not add any power because there is no time constraints or any restrictions on the prover. It can take all its time to make the computation because it's all powerful. So randomization or any such resource for that matter is not going to make it more powerful. For example, giving it more space or more time is is not going to affect. Okay, so any language that could have that can be uh, accepted by this IP star um, can also be accepted with a deterministic proof. Okay, so the other natural questions that arise with respect to the model, um, one is why are we only making the verifier randomized? Why can't we make the prover randomized? Well, if we do, it's still as powerful. So prover randomized, then it's the same as IP. Another question to ask here is, when we defined IP, there were certain success probabilities or error probability that we associated with it. So what was that? We said that if X is in the language, we want to accept with 2/3 probability. If X is not in the language, we want to reject with 2/3 probability. So where is this choice of success probability coming from? For example, if I make it uh, instead of error being 1/3, if I make error 1/4, is this new protocol with a lesser error probability strictly more powerful than IP? Or instead of 1/4, we can think of 1/n or some other error probability. It turns out that the same idea that we saw for BPP was also defined with respect to these probabilities, and we saw in detail why is that the case. That because uh, if the success probability is at least 2/3, we can amplify the process by repeating the random experiments again and again and improve the success probability. In fact, we can get the success probability boosted to 1 in this case when X is in the language. So the model of IP where uh, the if X is in the language, then the probability that the verifier prover accepts X is equal to 1, and if X is not in the language, then the probability that the verifier prover um, accepts X is at most 1/3. This is so although from 2/3 we have improved this probability to 1, this new protocol, this new class is again as powerful as IP. So it turns out that this also does not add any power to the model. Okay, so this is similar to the one-sided, I mean this definition is similar to the one-sided error definition of the complexity classes, the RP and so on, that we saw. Okay, okay, so yeah, there are several other questions that one can think of in the definition of IP. If we tweak some parameters here and there, tinker it, and ask uh, is if whether the new model is now more powerful or less powerful with respect to IP. We can tinker with the number of rounds or the success probabilities. These are few things that we saw. You can also think of other modifications. Okay, so hmm. Okay, so just to give an example, I think um, one such example that you've done in class is graph non-isomorphism or GNI. Okay, which is that given two graphs G1 and G2, yeah, given two graphs G1 and G2, you want to check whether G1 is isomorphic to G2. If G1 is not isomorphic to G2, then you want to say yes. If G1 is isomorphic, then you want to say no. Okay, so this is the complement of the graph isomorphism problem, which is in NP. This problem, however, is in co-NP. Okay, so okay, so the IP protocol, the IP that we saw for this particular problem was basically that we were choosing one of G1 and G2 at random, uniformly at random, choosing a permutation for the chosen graph and asking the verifier whether which graph is it isomorphic to. Is it isomorphic to 1 or is it isomorphic to 2? And we repeated this process. So notice that in that process, if X is in the language, that is G1 is not isomorphic to G2 for the yes instance, then the probability that the verifier accepts was always 1. So this is what we were maintaining. And in the other case, we had a small error probability 1 over 2 to the n or something, which was exponentially small. But yeah, just to recall that this example did maintain the fact that for the S instance, the verifier is correctly able to detect the S instances. Okay, so yeah, that brings us to the third question. So recall that earlier we stated, we saw this diagram that BPP is contained in IP. IP also contains NP, and turns out that IP is contained in P space. In fact, these two are equal. Okay, so if you want to show that P space is contained in IP, then it's sufficient to show that that a p-space complete problem is an IP. So one such p-space complete problem is our favorite problem, which is TQBF, total quantified Boolean formula. It's sufficient to show that TQBF can be simulated by an IP with polynomial number of rounds. So this is what Shamir proved in 1992. And the other direction, which is that IP is contained in P space, this is something that is easy to see. So we will look into this, we'll expand on this. This is something that will not do right now. I'm not sure if this was done in the lectures, but if you're interested, you can search for this paper by Shamir, which shows that TQBF is an IP. Okay, so yeah, so we'll prove that IP is contained in P space. So recall that IP here is those set of languages where there's a set of transcripts between the verifier and the prover. There is an exchange of messages where the verifier is randomized. Okay, and at the end of the day, if x is in the language, the verifier must accept with good enough probability. If x is not in the language, we want it to reject with good enough probability. Now, in order to show that IP is contained in P space, we need to show that any such algorithm, any such language which is in IP can be simulated by a deterministic Turing machine using polynomial space. Okay, so essentially for any interactive proof, we want to be able to simulate all of this using P space. Okay, if we could show that, then that means IP is contained in P space. So the idea is that we want to simulate the verifier in P space. Okay, so if the verifier were deterministic, then this only corresponds to the choices of the prover. So let's say the verifier asks a certain query to the prover. Okay, at this point the verifier asks a query. The prover may uh, the prover may respond with um, possible messages. For each of these messages, because the verifier is deterministic, there is a fixed. So these are the answers by the prover, and for each of this, the verifier has next query. Okay, based on which the prover could potentially have several responses. Post which the verifier has a single query to ask. So this the branching out that happens in this tree is happening only from the prover side because the verifier is deterministic. But now, if verifier is were randomized, that is the verifier tosses random coins, which is what happens in our case for IP. So this is a randomized verifier. So for every response of P is going to toss some random coins and send that query to the prover. Now for each of these tosses, the answers of provers could be different. So there is more branching out that could happen at each of these stages. Okay, so what this will look like is that, suppose assuming that the verifier speaks first, based on the random choices that the verifier makes, there are several queries that the verifier could have sent to the prover. And because the prover is all powerful, there could be several answers uh, that they could choose to answer, and further the verifier tosses random coins, and so on. So now this tree has more branches that are corresponding to the randomness of the verifier. Okay, so how large could this tree be? Okay, all we know for now is that each of these messages is bounded by polynomial. This is because the verifier runs in polynomial time, so we cannot afford for the queries to be larger than polynomial in length. So although this looks like this could be an arbitrarily large tree, there are several restrictions that we can put on the um, uh, on the uh, on the tree. So that means that the depth of this tree cannot be more than polynomially large, because there are several exchanges that are happening. This is a this is an IP with polynomial number of rounds. Each round corresponds to adds a depth of 1, adds a height of 1 to the tree. Since there are only polynomially many rounds, we are guaranteed that the height of this tree cannot be more than polynomial. Okay, now the question is, how many leaves can there be? So let's say we are talking about this last level. How many trees can there be? Well, each of the messages could be polynomial in length. So potentially the leaves could be all possible strings of polynomial length. So how many strings are there? There are 2 to the n to the c um, many strings of poly length. Okay. So although the depth of the tree is guaranteed to be polynomial, the number of leaves together, this could be exponentially large. Okay. So we can't just uh, we can't just go through this tree one by one, go in the breadth first fashion, and finally look at the last layer and count how many of them were saying accept and how many of them were saying reject, and then see if there are at least 2/3 of them that are saying. So at the end we're gonna have decisions that accept, reject, and so on. So the idea is that simulate each branch and the decision is made at the nodes. So if at least 2/3 of the nodes say accept, then we are going to accept, and if at least 2/3 of the nodes say rejects, then we are going to reject. The question is, what if the number of yeses or the number of accepts is less than 2/3 and more than 1/3? Well, that cannot happen. If x okay, let's forget about yeah, let's forget about this. Okay, it can okay, we'll talk about it later though. Okay, so this is what we want to do. Now the question is, how do we simulate this? Because we want to be able to do all of this in polynomial amount of space. So if we blindly do this, we blindly simulate this, we may end up taking exponential amount of space if we don't do it carefully. Just a naive implementation of this. Could take poly exponential space. Okay, so okay, so we want to do this carefully, or is there a clever way of implementing this? Find the counter, how whether at least 2/3 are saying accept or reject. Can we do this in a space effective manner? So what is the idea? The idea is that we want to somehow reuse the space. Okay, so notice that you don't really need to store the information of all the nodes, whether which node is accepting and so on. All you need is a count, because the decision is only going to be made based on what the count is. Okay, so yeah, so the count can be stored using polynomial space. This is because although the count could be as large as 2 to the n to the c, that is exponential, the binary encoding of this will anyway take polynomial amount of space. So this count can be stored in polyspace. So we don't need to worry about how do we store such a large value. So now we can use this fact that all we care about is the count, and we can forget all the information uh, prior to it. Okay, so what we'll do is we can do a simple DFS algorithm, that is explore the first branch, the leftmost, take all the lefts and get to the leaf, and if it says accept, then we will increment the counter. If it says reject, then we don't increment the counter. Then forget about this node, forget about this leaf, and explore the next branch. Okay, so we're going to go through all of these leaves in using DFS. So and otherwise you don't change the counter, and initially of course the counter is set to 0, and yeah, and at the end we are going to check if the once all the paths are exhausted, check if the counter is at least two-thirds of the total number. If yes, then we're going to accept. If not, then we're going to reject. Okay. um Hi, Goel.
Hi, good evening.
Good evening. So actually I started off the session at 6 p.m. and I'm done with all the questions though.
Okay, okay. Yes, yes.
Okay, so
No
let
issue.
me
No
just
issues. I will. Yeah.
end the recording. Okay, I'll have a chat with you.